Okay, so now let's do a couple of questions related to miscellaneous examples. Miscellaneous examples. Miscellaneous. Miscellaneous examples. Now, example number 26. Example number 26. We have if A is equal to what cos theta sine theta. I think I need to restart this software. Okay, so we have basically if A is equal to cos theta sine theta, negative sine theta, and cos theta, and you want to prove that A raised to the power n is equal to cos of n theta, sine of n theta, negative sine of n theta, and cos of n theta, n belonging to the set of natural numbers. So the way that we can prove that is that well, of course, if you multiply this matrix by itself, for example, what you will get is A squared is the same thing as cos theta sine theta, for example, times negative sine theta and cos theta, and multiplied by itself again, cos theta sine theta, negative sine theta, and cos theta. And that's the same thing as basically cos squared theta minus sine squared theta, cos squared theta minus sine squared theta, and basically cos theta sine theta, cos theta sine theta, plus cos theta sine theta. Of course, that's not the way to prove it, but let's see what happens. Then you have negative sine theta cos theta, negative sine theta cos theta, and then you have negative sine squared theta plus cos squared theta. And that is the same thing as now cos squared theta minus sine squared theta is equal to I have to take a look at my notes, and we will go to chapter 2, trigonometric functions, and not here, I'm not here, I'm not here. Okay, cos squared x minus sine squared is cos 2x. Okay, so you know that basically cos 2x is equal to cos squared x minus sine squared x. That's standard formula that we have done before. It is also equal, cos of 2x is also equal to 2 cos squared x minus 1, and that's also equal to 1 minus 2 times sine squared x, and it's also equal to basically 1 minus tan squared x over 1 plus tan squared x. So that's basically all the different ways of that, all the different ways in which we have written this formula. So cos of 2 theta is cos squared theta minus sine squared theta. That means that I can write basically cos squared theta minus sine squared theta. I can write it as cos of 2 theta. And this is the same thing as basically cos theta sine theta plus cos theta sine theta. That is 2 times cos theta sine theta. And that is negative 2 times cos theta sine theta. And that is the same thing as cos squared theta minus sine squared theta, which is equal to cos of 2 theta. And then you can write this as 2 times cos theta sine theta is the same thing as, you know, that sine 2x is equal to 2 times sine x cos x, right? So that means that this is basically, that is sine of 2x. So I can write this as basically cos 2 theta, and I can write this as sine 2 theta, negative sine 2 theta, and cos 2 theta. And I suppose here now what we have is, well, we kind of got the same thing for basically a squared. We got the same result. Cos of this is equal to a squared. So this is cos of 2 theta, sine of 2 theta, negative sine 2 theta, and cos 2 theta. Now let's see how they have actually proved it. So in order to prove this, mathematical induction. Okay, good. So basically what we have here is, because such things is the only way to prove such things is actually mathematical induction. There is no other way to do it. And so let's try to prove this using mathematical induction. So in mathematical induction, you always have basically, in case you're not familiar with the way that mathematical induction works, it's like, for example, you have an n number of books put on their back, basically. For example, you have this book over here, and you have another book over here, and you have another book over here, and you have another book over here, all the way up to, and these are all books laid on their backs. And all the way up to basically some book that you have over here. This is, basically n books over here. Now, the way that the principle of mathematical induction works is that I'm going to prove that, I'm going to show that, first of all, basically, you know that if the first book, if this book over here falls over, it will basically make the second book fall over, and the second book will make the third book fall over. The third book will make the fourth book fall over, and so on and so forth, until the nth book falls over. That is, of course, provided that the first book falls over, and each book that falls over as a result of that, the next book falls over. So there are basically two conditions here. Number one, the first book has to or must fall over. I'm going to have to show that the first book falls over. Second, as a result of each book falling over, and this is very important, as a result of each book falling over, the book next to that or after that, the book after that will inevitably fall over. Will inevitably fall over. Right? So basically the first book falls over, and as a result of each book falling over, the book after that will inevitably fall over, and from this you can conclude that the conclusion of this situation would be that the nth book will fall over, will inevitably fall over. So that's basically how the principle of mathematical induction works. So in the principle of mathematical induction, I'm going to have to show that basically for whatever sort of situation that I have, that the first case, meaning that the first book falls over. So that means that the first case, we usually call this P of 1. In the language of mathematical induction, we call this P of 1. And so that means that I need to show that this is true, meaning that the first book falls over. And then I need to show that for every book falling over, that the book next to that or the book after that falls over, meaning that I'm going to assume that, for example, some P of K is true, meaning that some book falls over, and any book, that means that some book means any book. Any book falls over, then I'm going to show that P of K plus 1 is true. Now this means that any book falling over, the book after that will inevitably fall over. And I've already shown that the first book has already fallen over. That means that, and then from this, I can conclude that P of n is true, which means that basically the nth book has fallen over, right? That's basically how the principle of mathematical induction works. And it works in the case of, in the case of situations where you have, for example, an n number of objects. For example, you want to prove something for the whole set of natural numbers. Of course, you cannot sit and show that every case for the set of natural numbers is true, because the set of natural numbers has an infinite number of elements. And so you have to use this kind of automatic process. And using this, you can show that, for example, some property or something, whatever that might be, is true for the whole set of natural numbers from the beginning all the way up to the end of natural numbers. So now let's do this. Let's do it. Let's. So first of all, P of 1 is supposed to be true, meaning that first to show that P of 1 is true, P of 1 is true, we have, so P of 1 means that basically n is equal to 1, n is equal to 1, that means that I have to show that basically, we want to show that that basically a raised to the power 1 is equal to basically cos of theta sine of theta negative sine theta and cos of theta, right? So so now what is how do I calculate a raised to the power 1? A raised to the power 1 is simply true, because a is equal to cos theta sine theta negative sine theta cos theta, and this is already a raised to the power 1. Therefore, P of 1 is true, right? So P of 1 is true. Now I want to assume that step number 2, I will assume that P of k is true, meaning that for some k, basically the relationship still holds, meaning that I'm assuming that I'm assuming that p raised to the power k is equal to cos of k theta sine of k theta negative sine of k theta and cos of k theta. That is basically P of k. I'm going to assume that this is true, and then using this assumption I'm going to have to show that we need to show that basically P of k plus 1 is true, right? Which means that P of k plus 1 would be P raised to the power k plus 1, and that would be basically cos of k plus 1 times theta sine of k plus 1 times theta, and then you have negative sine of k plus 1 times theta and cos of k plus 1 times theta. That is basically what I want to show. Now let's see how we can do that. Okay, so now basically in order to show that P of k plus 1 is true, meaning that P of k plus 1 is actually equal to this expression or this matrix over here, I'd have to take P of k and multiply it by P, right? And multiply it by the matrix itself. So meaning that P of k plus 1, P of k plus 1, I can say that, or I can simply write it as A of, for example, A of k plus 1, A raised to the power k plus 1 would be equal to A times A raised to the power k plus times A raised to the power 1, of course. Now A raised to the power k is equal to this P of k is basically this matrix here, which is basically cos of k theta sine of k theta and negative sine of k theta and cos of k theta, and multiply this by A, which is basically this matrix here, cos, sine, negative sine, and cos. Cos, sine, negative sine, and cos. Cos, sine, negative sine, and cos, and all are for theta. Now if you do this multiplication, what you will get is basically a matrix cos k theta times cos theta, cos k theta times cos theta plus basically, or actually minus so you have this row times this column, which gives you minus sine theta sine, or sine k theta sine theta, and then you have the same row times this column, which gives you cos k theta times sine theta, cos k theta times sine theta, and plus sine k theta times cos theta. And then the second row times the first column, you have negative sine k theta times cos theta, and minus cos k theta times sine theta, and cos k theta sine theta, and then this row times this column gives you negative sine k theta sine theta, and then this one times this one is going to be cos plus cos k theta cos theta. Now this is the same thing as cos k theta cos theta minus sin k theta sin theta. That is the same thing as basically cos of cos x cos y minus sin x sin y. That is the same thing as cos of x plus y, right? So x plus y. So I can write this as basically cos of x plus y, meaning k theta plus theta. So that is the cos of k theta plus theta. Now cos k theta sin theta plus sin k theta cos theta, you have basically, you know that cos x sin y plus sin x cos y is equal to sine of x plus y, right? So I can write this as sine of k theta plus theta. Over here, if I take a negative out, I'll end up with sine k theta cos theta plus cos k theta sin theta. So cos k theta sin theta, sin k theta, or I can say that, for example, okay, so I can call it, for example, cos theta. I can call it cos theta sin k theta, and I have a negative sign over there, I don't forget, plus sin theta cos k theta, which I can, based on this formula, I can write as basically sine, for example, theta plus k theta, right? And so that becomes negative sine theta plus k theta. And this one over here is cos k theta cos theta minus sine k theta sin theta, which is again the same thing over here, cos of k theta plus theta. So that is cos of k theta plus theta. And therefore you have this matrix. Now cos of k theta plus theta is the same thing as if I take a theta out, you'll get theta times k plus 1. So you can write this as cos of theta times k plus 1, which is, I suppose, what we were, yes, this is what we were looking for here. and this becomes sine of theta times k plus 1, and this is negative sine of k plus 1, for example, times theta, and this becomes cos of theta times, for example, k plus 1. Right, so that is basically that. So what that means is that basically this is the same thing as a of k plus a raised to the power k plus 1. A raised to the power k plus 1. So since a raised to the power k plus 1 is equal to p of k plus 1, so basically what I have done is that I have used basically I have used basically I have used my assumption here, and using my assumption I have assumed that p of k is true, and therefore, and using this calculation here, I have shown that basically p of k plus 1 is also true. Therefore, p of k plus 1 is true. So basically here we know that p of 1 is true. Here we have assumed that p of k is true. Here we have shown that p of k plus 1 is true, right? And therefore you can say that therefore by the principle of mathematical induction, we have, so over here we have basically so p of 1 was this expression. P of k plus 1 was basically a raised to the power k plus 1 was k plus 1 times theta, and therefore we can say that we have a raised to the power n is equal to basically cos of n theta and sine of n theta and negative sine of n theta and cos of n theta. So, and which basically holds for all natural numbers. So that is basically, that was question number 26. Now, question number 27, we have, if A and B are symmetric matrices of the same order, example number 27. If A and B are symmetric matrices of the same order, if A and B are symmetric matrices of the same order, then show that AB is symmetric if and only if and only if A and B commute that is AB is equal to BA. We want to show this. Okay, so now to prove this example 27, we are given that A and B are symmetric matrices of the same order, right? So which means that what the given in this example, it's important to know what you have been given so that you can work with it. So you have been given that basically A and B are symmetric matrices of the same order. Now you want to show that, you want to prove that basically AB is symmetric. AB is symmetric if and only if means by conditional, if and only if A and B commute, meaning that AB is equal to BA. AB is equal to BA, right? Now you need to, these biconditionals, you need to prove them basically individually, meaning that you need to prove that. So part 1 of the proof would be basically to prove that basically AB is symmetric. AB is symmetric if AB, meaning that this implies that AB is equal to BA. And then the other way around, meaning that if that is true, then meaning that this implies the other side. So part 2 of the proof would be to prove that basically AB is equal to BA implies that basically AB is symmetric. So what that means is that if you can prove both of these two statements or both of these conditionals, that means that you have proved this biconditional, which means that basically the combination of these two conditionals becomes this biconditional. So then proof part 1. So then proof part 1, you have basically, you know that A and B are symmetric matrices of the same order, and you want to prove that basically AB is symmetric. AB is symmetric implies that AB is equal to BA. Now, this is in the form, this is basically in the form P implies Q. Right? So this is, you can take this statement as P, and you can take this statement as Q, and this is in the form P implies Q. Now, to prove a statement of this form, P implies Q, or P if only Q, you can call it you can basically read it in many different ways, but that you can read it as P if P then Q. You can call it, for example, you can call this, if you have basically something like this, you can call it if P, you can call it if P then Q, you can call it P implies Q, P implies Q, you can call it P only if Q, only if Q, you can call it, I don't know. There is a couple more, even a couple more ways to do that. Now what that means is that, first of all, you need to understand what that means so that you know how to prove it. I mean, usually people don't have a good understanding of this sort of statement. So for example, let's say that I say that a number is a multiple of 9 if, or you can, let me write it this way. I can say that basically if a number is a multiple of 9, if a number is a multiple of 9, then for example the number is a multiple of 3. So what that means is that, for example, let's say that 18 is a multiple of 9, because 2 times 9 is equal to 18. Now 18 is, of course, a multiple of 3. For example, 27 is a multiple of 9. 27 is also a multiple of 3. 81 is a multiple of 9. 9 times 9 is equal to 81. 81 is also a multiple of 3. 3 times 27 is 81. And so on and so on. So this statement seems to be true, right? Now, so I can call this statement P, and I can call this statement Q, and what this is telling me is that if P then Q, right? If P then Q. Now what this means, what this statement means, it's telling me that basically if a number is a multiple of 9, then the number is necessarily a multiple of 3. And we say that basically Q, if you have some condition in the form P then Q, then you say that Q is a necessary condition for P. Condition for P. And you say that P is a sufficient condition for Q. Now if you learn one of them, it's more than enough. So you can learn, for example, the first one, which is Q is a necessary condition for P, meaning that if P is true, then Q must necessarily be true, meaning that if a number is a multiple of 9, then the number is necessarily a multiple of 3. There is no other way. It's actually not possible that the number is a multiple of 9 and the number is not a multiple of 3, because a 3 is nothing but a 9 is nothing but 2 3's, right? So if you put 2 3's together, you'll get a 9. That means that, and then you can multiply that 9 by whatever you want and you get some multiple of 9. That means that whatever your number, if there is a 9 in it, there is at least 2 3's in it, right? So which means that if a number is a multiple of 9, it is necessarily a multiple of 3. So now in order to prove this statement, what I'm going to do is that I'm going to assume that basically the number is a multiple of 9, right? I'm going to assume that a number is a multiple of 9 is a multiple of, my pen is, I think I need to change the tip. Assume that the number is a multiple of 9. In other words, I'm going to assume that P is true. I'm going to assume that P is true, and then I'm going to prove that based on that assumption, I'm going to prove that Q is true. Then I'm going prove that when I assume that the number is a multiple of 9, then I will prove that the number is a multiple of 3. Then prove that the number is a multiple of 3. Or in other words, you can say then prove that Q is true. Right? So what that means is that if you have a statement in the form P then Q, or P implies Q, or if P then Q, then what you will do is that you will assume that P is true, and then using that assumption, you will prove that Q is true, right? And I'm sure you will understand this, of course, because at least in the case of Indians, I have seen that I have been in India for like few years, like 4 years, and I have seen that Indians are, well, pretty smart. So these are not, of course, rocket science. Anybody can understand them. Meaning that what I'm saying here is that if I'm going to assume that the number is a multiple of 9, and then using that assumption, I'm going to prove that the number is a multiple of 3, and that way I have basically proved the conditional. Okay. Now, so let's do that. So let's do that, and so here basically what I have is that P implies Q, and P is AB is symmetric, and I want to show that basically AB is equal to BA, right? So now what I'm going to do is that I'm going to assume that P is true. In other words, I'm going to assume that basically AB is symmetric. AB is actually symmetric. That is the assumption that I make. When I say that AB is symmetric, that means that when we said by definition when a matrix is symmetric, the transpose of the matrix is equal to the matrix itself, meaning that you can write AB whole transpose is equal to AB, right? AB whole transpose is equal to AB. And this is the assumption that I make. And using this assumption, I want to prove that basically AB is actually equal to BA. Now you know that basically the proof would be as follows. You can write your assumption here. The assumption that you have is AB whole prime is equal to AB, and so of course AB whole prime, you know that it's equal to B prime times A prime. We have already proved this. That is equal to AB. Now we know that basically A and B are both symmetric matrices. Symmetric means that the transpose of A is equal to A, the transpose of B is equal to B. So I can write this as B times A is equal to A times B. and that is because A and B are symmetric matrices. And that is basically the first part of the proof. Here basically you can see that AB whole prime is actually equal to basically we have made the assumption that AB whole prime is equal to AB, and that shows that BA is equal to AB, meaning that if AB is symmetric, then A and B commute. Meaning that what this means is that if basically AB is symmetric, which is this condition here, AB is symmetric. If AB is symmetric, then A and B commute. Right, so that is one thing. Now, this is only one part of the proof. Proof part 2. So, proof part 2, you want to show that, to prove that basically AB is equal to BA implies that AB is symmetric. AB times AB is equal to BA implies that AB is symmetric. Right? So now again what I will do is that I take this as some statement P, I take this as some statement Q, and this is basically P implies Q. Right? Now the assumption that I will make is that P is true. In other words, I will assume that AB is equal to BA. AB is equal to BA. And to prove that AB is symmetric. AB is symmetric means that AB whole prime is equal to AB. Meaning that the transpose of the matrix is equal to the matrix itself. So now the proof is as follows. You can say that basically the assumption is AB is equal to BA, and if I take the transpose of both sides of this equation, I will get AB whole transpose is equal to BA whole transpose. And so you know that basically I write this as AB whole transpose is equal to, this is A transpose B transpose, and you know that A transpose is equal to A and B transpose is equal to B. So this is equal to A times B, meaning that AB whole transpose is equal to AB because A transpose is equal to A and B transpose is equal to B. And the reason for that is that basically A and B, in the beginning we said that they are symmetric matrices. And therefore, basically this is what we wanted to show. We wanted to show that AB is symmetric, and this is the assumption that I have made is that A and B commute. So here now I can say that basically if A and B commute, then basically AB is symmetric. AB is symmetric. Now, over here we said that if AB is symmetric, then A and B commute. And over here we said that if A and B commute, then AB is symmetric. Therefore, you can put the whole thing together and say that basically if A and B commute, or you can say it the other way around, if if AB is symmetric, for example, if AB is symmetric, then, not then, if and only if A and B commute. And if and only if, as you know, means bidirectional, or biconditional, I'm sorry, biconditional. So that's how you would solve such a problem, which is the kind of thing that I actually like a lot. I like mathematical logic. So let's do, there is only one example left here. Let's do that one as well, and then we will finish this video. Okay, so the next question is question number 28. Example 28, which is A is a matrix as 2, -1, 3, and 4, and B is a matrix as 5, 2, 7, 4, and C is a matrix as 2, 5, 3, 8. 2, 5, 3, 8. Find the matrix D such that CD minus AB is equal to O. Okay, so to find that matrix, of course it has to be a matrix of 2 by 2. Let's define D as, for example, ABCD, and if that is the case, then we have, well, CD minus AB, we have CD minus AB is equal to O, meaning that C is basically 2, 5, 3, 8 times D, which is ABCD, is equal to minus A times B, which is 2, -1, 3, 4 times B, which is 5, 2, 7, 4. 5, 2, 7, 4 is equal to 0, 0, 0, 0. Now we need to basically calculate these separately, meaning that, okay, I think it seems that I made a mistake somewhere over here, and I need to basically calculate everything again. So now let me actually go back here. These are old. There is a mistake in here. I have to take that. So let me check my matrices. 2, 2, 5, 3, 8, AB, ABCD minus 2, -1, 3, 4 times 5, 2, 7, 4 is equal to this. So here we have no problems. So now if I calculate this one, basically this row and this column, I'll get 2A plus 5C, and then I get 2B plus 5D, 2B plus 5D. Then this row and this column, I will get 3A plus 8C and 3B plus 8D, 3B plus 8D, minus over here I will get basically this row and this column. I get 2 times is equal to 10 and -7, and over here I get 2 times is equal to 4 minus 4, and over here I will have 3 times 5 is equal to 15. 4 times 7 is equal to 28. That is a positive 28. And 3 times 2 is equal to 6. And 4 plus 4 times 4 is equal to 6. And I don't know why I have written negatives here. And therefore, this is going to be 2a plus 5c, 2b plus 5d, 3a plus 8c, 2b plus 5d, 3b plus 8d, minus 10 minus 7 is equal to 3, 4 minus 4 is equal to 0, 15 plus 28 is equal to, let's say, 30 plus 14, 45, 43, that's positive 43. And 6 plus 16 is equal to 22. Positive 22. And so basically you have 2a plus 5c minus 3. You have 2b plus 5d. 2b plus 5d. 3a plus 8c. Minus, that is positive 43. So minus 43. So 3a plus 8c minus 43. And over here you have 3b plus 8d minus 22. So this is a positive 22. So this becomes negative 22. This becomes negative 22 is equal to 0. And then based on that we will get some equations. So 2a plus 5c minus 3 is equal to 0. Equation number 1. 2b plus 5d. 2b plus 5d is equal to 0. Equation number 2. 3a plus 8c minus 43 is equal to 0. Equation number 3. And 3b plus 8d minus 22 is equal to 0. Equation number 4. Equation number 4. Now these equations I have. So a and c, I can take these two equations, for example 1 and 3. And so I have basically 2a plus 5c is equal to 3, number 1, and 3a plus 8c is equal to 43, equation number 3. Now, I want to cancel these a's out. So I want to get the, for example, over here, I want to get to get the coefficient of a to be negative 3 so that it cancels out with positive 3. So if I multiply 2 by some number to become negative 3, x would be negative 3 halves, which means that I multiply 1 by negative 3 halves. So I will have 2 times negative 3 halves would be negative 3a. 5 times negative 3 halves is negative 15 halves. Negative 15 halves c is equal to 3 times negative 3 halves is negative 9 halves. And then I will write 3 as it is. I will write 3 as it is, meaning that I write 3a plus 8c is equal to 43. That is basically my equation, that's my system of equations. And therefore, these two will cancel out, and you will have negative 15 halves plus 8 times c is equal to negative 9 halves plus 43. And let's calculate these over here. So negative 15 halves plus 8 is equal to 2 negative 15 plus 16. So that's equal to 16 minus 15 is equal to 1 half. So 1 half c is equal to negative 9 halves plus 43, which is equal to 2 negative 9. 2 times 43 is equal to 86. 86 minus 9 is equal to 77 halves. That's equal to 77 halves. Which means that if I cancel these two out, C is equal to 77. Now that is actually the right answer. The first time I didn't get the right answer. Now, if I use any of these equations, for example, number 3, I can write 3a plus 8 times 77 is equal to 43. And that means that basically 8 times 77 is, I don't know, 77 times 8 is equal to 56. 56 plus 5 is equal to 61. 616. So that is, goes to the other side, becomes negative 616 plus 43. So what is 616 minus 43? And you have a negative sign there, we don't forget it. So 63 and 11 minus 7 is equal to, minus 4 is equal to 7, and that's 573. That's negative 573. And here you have 3a. I don't know if this number is 10, 15. So this number is divisible by 3 because 3 plus 7 is equal to 10. 10 plus 5 is equal to 15. 15 is divisible by 3. Therefore, the number is divisible by 3. So 573 divided by 3 is equal to 1 times 3 is equal to 3. 9 times 3 is equal to 27. And 1 times 3 is equal to 3. So that's basically a is equal to negative 191. Negative 191. Which is actually the correct answer. Now, we need to basically create another system of equations for B and D, which is equations 2 and 4. These two. So I make a screenshot here and put this over here on the other over there. And so equations number 2 and 4, we have basically 2b plus 5d. 2b plus 5d is equal to 0, and 3b plus 8d is equal to 22. This is number, one of them is number, this is number 2 and this is number 4. Now, again, I divide by 3 to get it to 0. I'm sorry, divide by 2 to get it to 0, then multiply it by negative 3. So, negative 3 halves, 2 times negative 3 halves is equal to negative 3. And if I make this coefficient negative 3, then they will cancel out. So I will multiply this whole equation by negative 3 halves. Which means that 2 times negative 3 halves gives basically 2 times negative 3 halves is equal to negative 3. So that's negative 3b. 5 times that negative 15 halves. Negative 15 halves d is equal to 0. And that is number, well, let's not write the numbers anymore because they have changed. And 4 gives basically 3b plus 8d is equal to 22. Now I will add these together. These two will cancel out. We'll have negative 15 halves plus 8 times d is equal to 22. 22 plus 0 is equal to 22. So now negative 15 halves plus 8 is equal to 2 negative 15 plus 16. So that's 1 half. So 1/2 d is equal to 22, which means that multiply by 2 you will get a d, and that's d is equal to 44. And that is d. And then if I take equation number 4, for example, that gives 3b plus 8 times 44. 8 times 44 is equal to 22. 8 times 44 is equal to 8 times 4 is equal to 320, and 8 times 4 is equal to 32. Add them together, you'll get 2, 5, 3, 352. Goes to the other side, becomes negative 352. And 352 minus 22 is equal to, and have a negative sign there, 0, 3, 3, that's negative 330. And that is 3b. And then this number is also divisible by 3, because 3 plus 3 is equal to 6. 3 plus 3 plus 0 is equal to 6. 6 is divisible by 3. The number is divisible by 3. So 300, that's 3 times 110, of course. 1 times 3 is equal to 3. 1 times 3 is equal to 3. And 0 times 3 is equal to 0. Right? No, just the 0 comes over here, I'm sorry. So it's 110. 3 times 110 is 330. So that means that b is equal to negative 110. Right? And based on all of this, you can say that basically the matrix that we had, which we called D, was basically, we called it A, B, C, D. So that is equal to A was equal C 77, A negative 191, C 77, and D is, A is negative 191, negative 191, B is negative 110, and D is 44. And D is 44. That is the matrix that we were looking for. Okay, that was a long calculation. Okay, so now we have a couple of miscellaneous exercises. We will do them as well in the next video, and then we are done with this chapter. I know there are many people that have asked me to do a chapter on differentiability and continuity and that sort of thing, calculus. So then I'm doing my best to get there, but well, of course you have to go step by step, and you cannot go too fast, otherwise you would burn yourself out. So now I hope that you enjoyed this video. I will see you in the next video, and thank you.